here's the problem we left off with yesterday. We're going to start with the simple part, which is the name. Okay. So our cation is copper, so in the name, that comes first. So we're going to write copper. And then we are using the stock system naming, so since they told us that the charge is 2+, we're going to put Roman numeral 2 after the name copper. And then our anion is sulfur, so it's going to get changed to sulfide. Okay. So there would be your name for this compound. Then, if we want to figure out what this should look like, we simply put them next to each other with their charges. I wish it was easier to write on this. There we go. And then we cross over the charges to be the subscripts. So we would wind up with Cu2S2, which would leave us with a positive 4 charge and a negative 4 charge, which balances, so we know it's correct. But we then need to look at their greatest common factor to see if this can be reduced at all, and it can. So the formula should wind up just being CuS. Make sense? Awesome. Now we can move on to compounds that contain polyatomic ions. If you remember from polyatomic ions, that's a group of atoms that are covalently bonded together, but they have a charge. A list of the common polyatomic ions and their names can be found in your textbook on page 220. There's a little figure 1.3 that has a list of common ones and what you call them. Okay. Most of the common polyatomic ions that we're going to deal with are what are called oxyanions. Okay, you can break that down to mean that it is a polyatomic ion, it's negative because it's an anion, and it contains oxygen, hence the prefix oxy. Okay? So most commonly you're going to see negative groups of atoms that contain oxygen in some form. Some elements can combine with oxygen into more than one type of oxyanion. For example, nitrogen and oxygen can combine into NO2- and NO3-. So see how it can do more than one? The compound is given a name that depends on the number of oxygen atoms in it. So, whichever ion has a greater number of oxygen atoms in it is going to end with the suffix ate, or ate. And the ion that has the lesser number of oxygen atoms will end in ite. So, to give you an example of that, NO2 has the smaller number of oxygen atoms, so it is nitrite, and NO3 has the greater number of oxygen atoms, so it is nitrate. If an atom can form even more than 2 ions with oxygen, because there are some that can form 3 or 4, then we start to introduce prefixes. The prefix hypo is given to an anion that has 1 fewer oxygen than the ITE anion. And the prefix per is given to an anion that has 1 more oxygen atom than the 8 anion. I promise this will make sense in a moment. ClO is hypochlorite. ClO2- is just chlorite. ClO3 minus is chlorate, and ClO4 minus is perchlorate. So when you've got 4 like this, then you use those prefixes. If you only had 3, then you would do one or the other. So as you increase the number of oxygens, then you can change the names. This becomes important in the naming of ionic compounds, because if you are using this as your anion, then that name is what needs to go second in the naming. Compounds that contain polyatomic ions are named in the same way that binary ionic compounds are named. The name of the cation is given first, followed by the name of the anion. So for example, this has silver and then a nitrate ion, so it's silver nitrate. And then silver nitrite is written when you have the nitrite ion instead. Let's give this some practice. Okay. Write me the formula for tin 4 sulfate. Now, the ending doesn't tell you how many oxygens it has. It tells you comparatively. So you're probably going to need to look up in your book the formula for sulfate and also its charge, so you can figure that out. And then you know the charge of tin, so go ahead and try to write out the formula. All right, so to begin with, we're going to write them side by side. So the abbreviation for tin is SN, and then the 4 in parentheses tells us that this is the 4+ version of tin. And then we have sulfate, which if we look in the book is SO4, and then 2- is the charge on that. So just out of curiosity, what would that mean the formula for sulfite is?
SO3 2-.
Yes. So just 1 less oxygen. Okay. So now we're going to cross over the charges. So 2, and then we're going to put a little parentheses here for ourselves so we don't get the 4s confused. 4, okay. And that would leave us with 2 times 4 is 8, 2 times 4 is 8, so the charges match up, but is this reduced? No, what could we reduce this to? SN, SO4, 2. Can reduce it by dividing by 2. So tin 4 sulfate could be written like this. All right. Now let's talk about naming binary molecular compounds. So we've been focusing in on ionic. Now we're going to talk molecular. There are 2 styles of nomenclature, which is, again, the way we say naming systems for binary molecular compounds. Okay. The first one is called the Stock system, which we will discuss, but we're going to take separate time to discuss it. It's coming in lesson 2. And what we're going to discuss today is the prefix system. The prefix system is older, and because it's been around longer, a lot of the names of chemicals are more widely recognized in the Stock system. So a lot of chemicals that you've heard, like carbon dioxide and things like that, are the names of those chemicals in the Stock system, in the prefix system. So we're going to learn how to use the prefix system today. It's pretty straightforward. Both systems are acceptable, by the way. unless somebody specifies to you that they don't want you to use one of these systems in a paper you're writing, either version is acceptable, and people will know what you are talking about. The prefix system uses the prefixes which are found on page 222 of your textbook in figure 1.4. I would recommend flipping there because you're going to need them. They are pretty straightforward, okay? Mono, the prefix mono means one, di means two, tri means three, but then after that you may not be as familiar with things like tetra and penta and hexa and hepta. Octa might seem familiar for 8, right? So some of them will be familiar and some of them may not be as familiar. But those are the prefixes I'm talking about when I say use a prefix. The rules for the prefix system are as follows. Rule number 1, the element that has the smaller group number is usually given first. Okay, so if you were dealing with boron and beryllium, beryllium is in group 2, boron is in group 13, beryllium would come first. If both of the elements are in the same group, then whichever has the greater period number is given first. So if you're dealing with sodium and potassium, they're in the same group, they're in group 1, so you would look for who has the greater period number, and that is potassium, so then potassium would go first. Rule number 2, you only give the first element a prefix if it contributes more than one atom to a molecule of a compound. Okay? So you should never have a compound that starts with mono something, because if it only has one atom of that element, then you're not putting a prefix on it. Just like we don't put a subscript 1 in a formula if there's only one of those atoms. Rule number 3, the second element is named by combining 1, a prefix that indicates the number of atoms contributed by that element, 2, the root name of the element, and 3, the ending "-ide". With a few exceptions, the ending "-ide" means that the compound only contains 2 elements. So you wouldn't put the ending "-ide" on, sorry, if you had like 3 or 4 elements in your compound. We're just talking about binary molecular compounds, so all of the ones we do will have "-ide" on the end of them. And then the O or A at the end of a prefix is dropped if the word following the prefix begins with another vowel. And this is just to make things not clunky to read and write. Because if you were going to say there was 1 oxygen, you would say monoxide. So instead of writing monoxide, they just drop one of the O's and write monoxide. Instead of pentaoxide, we would drop the A and write pentoxide. Examples of the prefix system. Okay. N2O would be written as dinitrogen monoxide. So they added the prefix di to nitrogen to tell you that there are 2 of them. Then they added the prefix mono to oxygen, and then they changed the ending of oxygen to "-ide, so it is now monoxide. NO would just be written as nitrogen monoxide, because we do not put a prefix on the first one if there's only 1 atom of it. Then NO2 would be nitrogen dioxide, and N2O3 is dinitrogen trioxide. So see what I mean by being pretty straightforward after you get through the beginning of it? Okay, go ahead now and try the example problems. Oh, I forgot I put one more on here. Dinitrogen tetroxide. A few more, apparently. Okay, now you can give the example problems a shot, writing out the names for these and the formulas. So if we look at this first one here, we have arsenic and oxygen. Arsenic, there are 2 atoms of arsenic, which means we need a prefix, and the prefix we're going to use is di. Diarsenic. And then we need a prefix to mean 5, which is penta. But we're going to cut off the A at the end of penta because we have a element that begins with a vowel, so pent-ox. And then we are truncating oxygen and turning it into oxide. So diarsenic pentoxide. And then the formula for oxygen difluoride. The fact that there's no prefix on oxygen indicates to us that there's only 1 atom of oxygen in this. And then the di in front of fluoride tells us that we're dealing with 2, and we can deduce from fluoride that they really mean fluorine. All right. We've gotten through the naming. Now we're just going to talk a little bit about a couple of things. There's more information on both of these topics in your notes or in your book if you want to read about them. I'm just giving you a cursory view of them. Some covalent compounds are not individual molecules. Instead, they're networks, like ionic compounds are. Like in ionic compounds, the subscripts in these compounds would indicate simple whole number ratios for atoms and not actual numbers of atoms found in the compound. Okay? But the naming of them is still very similar to the naming for other molecular compounds, even though they are networks. You can see some examples of their names on page 224 in your book. An acid is a distinct type of a molecular compound. Most acids fall into one of 2 types. They can either be a binary acid. This is an acid that's made up of 2 elements. Usually one of those elements is hydrogen and another one is a halogen, so something from group 17. The other type is called an oxyacid, which you can guess from the name means that it contains oxygen. So it usually contains oxygen, hydrogen, and a third element that's most of the time a nonmetal. Because the special properties of acids are connected to their properties when they are dissolved in water, when we talk about an acid, like if I say we're going to use hydrochloric acid today, usually what I mean is we're going to use an acidic compound in a solution of water, not just on its own. There are exceptions, but usually that's what I mean. So if I say we're going to use hydrochloric acid today, what we're really using is hydrogen chloride that has been dissolved in water. Many polyatomic ions are produced when hydrogen atoms are lost by oxyacids. So when you dissolve an acid in water, it loses a hydrogen ion. And then what you're left with is a negative ion or an anion, and it's usually a polyatomic ion. So a lot of the polyatomic ions that we talked about earlier are the result of dissolving an acid in water. So for example, if you take sulfuric acid, which is H2SO4, and you dissolve it in water, then those hydrogen ions are lost and we are left with a sulfate ion. If you dissolve nitric acid in water, HNO3, then you're left with a nitrate ion. If you dissolve phosphoric acid, H3PO4, then you get a phosphate ion, and so on and so on. When a cation joins up with the anion from an acid, it produces a salt. So if you dissolve an acid in water, you're going to be left with these anions, and if those anions find other atoms to join with, or other ions I should say, cations to join with instead of the hydrogen ions they were originally joined to, the substance that you produce from that is called a salt. So outside of science class, when you tell somebody you're going to go pick up salt from the store, they assume you are talking about table salt. People who have not taken chemistry class think there is only one salt. That is table salt. Table salt, sodium chloride, is a salt, but it is not the only salt. There are many salts produced that you would not want to eat, but they have other valuable purposes, such as use in fertilizers or use in clearing ice off of roadways. So, example, when the chlorine ion from hydrochloric acid joins the sodium cation, you get table salt, sodium chloride. All right.